Hey folks, this is the fourth video in a multi-part series of short videos covering the concept of the tensor product in linear algebra. In the prior video, we introduced the tensor product from a universal point of view. In this video, we're going to prove that the tensor product actually exists. Let's get started. Let U and V be arbitrary vector spaces over a field F. How can we actually construct a tensor product for U and V over F? Let's explore the idea. Intuitively, a tensor like the one seen here behaves like a formal sum of pairs of elements of U and V, where the pairing operation is bilinear. Formal here means we're just talking about syntactic expressions. We're not adding pairs like we do in a direct product vector space. So the question becomes, how can we actually construct a space consisting of things like this? We first recall from a prior video in this series that the free space on the set U times V consists of all formal linear combinations of pairs of elements of U and V over F. As a reminder, this free space does not involve the direct product vector space U times V. U times V is just the Cartesian product set. In particular, the linear combination here is not equal to the pair seen here. This is useful to us in the present context because we're trying to construct a space with formal sums of pairs. However, the pairing operation is not bilinear in the free space. That is, in each of these equations, the pair on the left-hand side is not in general equal to the linear combination of pairs on the right-hand side. To obtain bilinearity, we would need to impose the relations seen here. That is, we would need to make the vectors on the left-hand sides of these relations become 0 for all scalars alpha and beta in F, all U vectors in U, and all V vectors in V. But we recall from the first video in this series that we can impose such relations by passing to a quotient space of the free space. To that end, let K be the subspace of the free space spanned by the vectors that we want to become 0. Then we define the space U tensor V to be the quotient space of the free space by K. And we define the element U tensor V to be the canonical projection of the pair UV in the quotient space. Intuitively, this quotient construction gives us bilinearity and nothing more, so we expect this to define a tensor product of U and V. And indeed it does. The map we defined is universal bilinear. To sketch the proof, I'm going to talk through this diagram. The curved arrow on top is the tensor product, which is the composite of the two arrows immediately below it, the inclusion function of the set U times V into the free space, followed by the canonical projection onto the quotient space. The arrow at left going down is an arbitrary bilinear map F from U times V to W. By the universal property of the free space, F extends uniquely to a linear map phi on the free space, which is the arrow going straight down in the middle. The key observation is that since phi and F agree on the pairs in U times V, and F is bilinear, it follows that phi kills the subspace K. Remember, K is spanned by the vectors which become 0 when the action on pairs is bilinear. By the universal property of the quotient space, then, phi factors uniquely through the canonical projection, yielding an induced linear map phi bar, which is the arrow at right going down. At this point, we've identified everything in the diagram, and we know that each part of the diagram commutes, so the whole diagram commutes. That shows us that F is the composite of the tensor product followed by phi bar, that is, F factors through the tensor product. Moreover, the uniqueness of phi bar for this factorization follows from the uniqueness of phi bar and phi in the universal properties for the quotient space and the free space. I'll leave that for you to ponder. In summary, this shows that the tensor product map we defined satisfies the universal property, as desired. This construction shows that the tensor product always exists. The construction is elegant, coordinate-free, and works in general. However, it doesn't immediately give us insight into what was actually constructed. For example, how large is U tensor V? We built a massive free space and then killed off a massive subspace to form the quotient space, but what's actually left over? In order to answer this, we first study more closely the case of free spaces. We have the nice result that the free space operation maps Cartesian products to tensor products. That is, the tensor product for free spaces is the free space of the Cartesian product of the sets. To prove this, we first observe that by the universal property of the free space on the Cartesian product, there's a unique linear map sending the pair xy in that free space to the tensor x tensor y in the tensor product space. It's easiest to see in this commutative diagram. The arrows on top and at left are both inclusions. Phi is induced from the composite of the inclusion on top followed by the tensor product at right going down. We claim that phi is an isomorphism. Indeed, phi is injective, since if 0 is the result of applying phi to an arbitrary element in the free space, where we here assume the pairs in the representation of the element are distinct, then by linearity of phi, that's equal to the linear combination of tensors seen here. By grouping terms with the same y value and using bilinearity of the tensor product, that's equal to the sum seen here, where the y's are distinct. Notice what's going on here. The outer sum is over the distinct y values in the set of all yi's from the pairs. And for each such y, the left component of the decomposable tensor with y is the sum of all the corresponding alpha I xi's. We're able to form those left components because of the linearity of the tensor product in its left input. Now it follows that all of the alphas are 0. That's because, first of all, those distinct y's are linearly independent in the free space, so we can apply the proposition on linear independence from the prior video to get that all of those linear combinations of the x's must be 0. And in each of those linear combinations, the x's are distinct, because we started with distinct pairs. The linear independence of distinct x's shows that the alphas in each linear combination are 0, and hence all the alphas are 0. On the other hand, phi is surjective since the tensor products of elements of x and y, which are in the image of phi, span the tensor product space. So phi is an isomorphism as claimed. It follows from this that the dimension of any tensor product space is the product of the dimensions of the spaces. This is called multiplicativity of dimension, and holds even for infinite dimensional spaces. To prove this, we can fix bases in the spaces to write them as free spaces. Here we're viewing the basis elements as elements of the free spaces, as described in the prior video on the free space. Then the result follows immediately from the proposition, as seen here. We use vertical bars to denote the cardinality of a set, which may be an infinite cardinal. But the proposition we proved actually gives us more information. It tells us that the tensor products of basis vectors are basis vectors. That's because the isomorphism in the proposition maps basis pairs in the free space to what must be basis tensors in the tensor product space. This corollary is useful for computation and gives us a more concrete sense of what we actually constructed. Before wrapping up, I want to make contact with another common definition of the tensor product. Let f be an arbitrary linear functional in the dual space of U, and let G be an arbitrary linear functional in the dual space of V. Then the map from the set U times V to the field F, sending the pair UV to the product F of U times G of V, is bilinear. That's just because F and G are linear and multiplication in F is bilinear. So by the universal property of the tensor product, this map induces a linear functional in the dual space of the tensor product space, which does the same thing to decomposable tensors. We write this functional as F tensor G. Now suppose that U and V are finite dimensional. Then it follows from multiplicativity of dimension that the map from the set U star times V star to U tensor V star, sending the pair FG to the functional F tensor G, is a tensor product. So the tensor product space U star tensor V star can be taken to be U tensor V star with this tensor product. The map here is clearly bilinear. The key to proving that it's a tensor product is showing that its induced linear map is injective, which takes a little work. But then multiplicativity of dimension shows that these spaces have the same dimension, so the linear map is also surjective and hence an isomorphism. We omit the details. Taking dual spaces on both sides of this equation and using reflexivity, that is, using the fact that a finite dimensional vector space is naturally isomorphic to its double dual, we obtain that U tensor V is naturally isomorphic to the dual space of U star tensor V star. And by the universal property of the tensor product, that's naturally isomorphic to the space of bilinear forms on U star and V star. This is commonly taken as a definition of the tensor product in the finite dimensional setting. As a definition, its virtues are that it's concrete and coordinate-free. However, without the universal point of view, the definition seems weird and unmotivated, and it can be more of a pain to work with in practice. You may encounter other similar definitions like this. Having watched these videos, you're much better positioned to understand where such definitions come from. In summary, we've seen in this video that the tensor product really does exist. It can always be constructed by forming a quotient space of a free space. We also saw that its dimension is multiplicative, and more specifically that the tensor products of basis vectors are basis vectors in the tensor product space. Finally, we saw that in the finite dimensional setting, the tensor product space can also be defined in terms of bilinear forms on dual spaces, or similar. In future videos on this channel, we'll make use of the tensor product in interesting ways. Stay tuned.